Hello, everyone. My name is Purab Sutradhar, and I'm a PhD candidate in the Department of Computer Engineering at Rochester Institute of Technology. So today I'll be presenting our paper, which is titled, um, sorry, Implementation and Evaluation of Deep Neural Networks in Commercially Available Processing and Memory Hardware. The hardware in this case is the UPMEM PIM. This paper was published in the SOCC conference back in 2022. So I'll start my presentation with a brief description of the concept of processing in memory and an overview of the UPMEM PIM hardware and its feature and its architecture. So next, I'll discuss the proposed CNN implementation in the UPMEM PIM. This discussion will involve the challenges of CNN implementation and how we overcame this and how we came up with our own solution. We'll also discuss the implementation of two CNNs in the PIM, which have contrasting scale and structure. And next, I will discuss the results of our implementation and provide performance analysis. Finally, we'll discuss some limitations in the UPMEM PIM hardware that we faced um, during the development of our projects and our take on how those can be implemented, improved. Yeah. So as I was saying, that processing in memory is a novel computing paradigm where we bring the memory inside the processor, which is a striking difference from the traditional John von Neumann's computing model, where CPU and the memory are separated. So the problem with that traditional approach was that the physical dimension of the bus that connects the memory and the processor is not efficient and therefore has a considerable latency and ohmic loss and above all a very narrow data bandwidth. So all of that together makes a memory bottleneck. And to overcome the memory bottleneck, most CPUs have cache, multiple layers or hierarchies of cache. However, when it comes to data intensive applications with very repetitive memory access, for example, transformers and other machine learning applications, the traditional processing architecture is not good enough because there is a huge amount of loss in energy from these data movements. And therefore, we are considering the alternative computing models that go beyond the von Neumann model. And such an example is the processing in memory. In this one, we don't need to move the data out of the memory chip because the processor itself is located inside the memory. And therefore, we have much less memory bottleneck and energy loss. And so there is a good motivation for choosing DRAM for developing such a processing architecture because it's a very mature memory technology and it's affordable and commercially feasible. But also it has a very high memory density, which is very favorable for large scale data intensive applications. And the DRAM die is more friendly towards the integration of digital circuits. So let's first have a look at what kind of like different ways that we have for implementing processing in memory. So a memory chip consists of multiple memory banks, and inside the banks there are multiple 2D memory grids called the subarrays, and inside subarrays there are bit lines and word lines that are connected to each cell. Now we can perform computation right next to the memory cells using the bit lines, and this is called a processing using memory. Next, we can also perform the computations outside the subarrays, but inside the memory bank. So this is another approach that we have pursued for a while now. And there's another approach where we can perform the computation outside the bank. So this is called the near bank processing, and the UPMEM PIM falls into this specific category. Now, the benefit of this approach is that since the processor is located outside the bank, you kind of have no limitation on the dimensional design of the processor. You can make it large, small, and adapt it to various kind of applications. So And that brings us to the UPMEM PIM. And to the best of our knowledge, this is the first memory-centric computing solution that has been made commercially available for use. And it features DRAM chips infused with DPUs that are trademarked RISC processors, that is reduced instruction set processors. And each DPU has an instruction cache called IRAM and a data cache called WRAM, and the whole setup is interfaced to the MRAM, which is essentially a DRAM bank. And each DRAM chip contains 8 DPUs, leaving 512 megabytes of onboard memory per chip. Also, multiple DRAM chips are combined together in a server configuration with SDK and toolchain for implementing large applications and implementing those in a distributed manner. So as this in this project, learning this tool chain was an essential part of our development. So when it comes to implementing the CNNs in the UPMEM PIM system, there are several challenges that we had to overcome. So first of all, that we chose CNNs because it's a very widely utilized deep learning application for image or audio detection. And since there are a large number of convolution operations, those are essentially parallel and therefore can be executed in a very distributed manner. So in the process of running CNNs in the UPMEM DPUs, there has been some challenges, as I was saying. So the first one was converting the CNN from its Python framework. So as we know, that CNNs are generally implemented in the Python framework, such as PyTorch or TensorFlow or Darknet. So we had to convert those Python codes to the C environment, since the DPU compiler does not support Python at this moment. And so when in this conversion, we had to work our way around some libraries such as the time-h and math-h in C. And so next thing we had to do is quantize the data precision of all the operations. Because DPUs support only low precision fixed point operations such as 8 or 16 bit computations. And at this moment, no floating point is supported. So we essentially had to convert the floating point into fixed point. And so other interesting challenge that came up during the work was that the data orchestration is done in 8-byte granularity. And so we had to align all data in 8-byte blocks, which was, we eventually overcame that, but it was a bit interesting in the beginning. So let's have a look at how we actually mapped the CNNs in the UPMEM PIM. So first, the CNN layers are decomposed into a stream of small tasks such as matrix, and matrix vector multiplications. All the convolutions are also converted to this stream of operations. And then these GM and GMV operations were distributed across many DPUs located in multiple DRAM chips. And the corresponding data of each such task was organized in the MRAM, ensuring proper data alignment. And this was done by the toolchain, actually. And finally, the instruction threads were fetched to the DPUs. And so inside the DPUs, the data is captured by the instructions are captured by the IRAM, that is the instruction cache, and then the data is fetched in and processed in a standard RISC processor architecture. So the first CNN that we implemented was the EBNN. Now, EBNN, it stands for Embedded Binary Neural Network. So the binary neural networks are a kind of highly quantized deep neural networks aimed at low precision computing. The neural weights of this network are binarized. That is, it's either 0 or 1. And this was highly helpful in reducing our resource overhead, and therefore it was possible to map many tasks across each DPU, since each computation was simplified. For example, like if you consider a multiplication with a binary weight, it is simplified to an addition or a subtraction. So so that's just BNN, but when it comes to EBNN, there's further modification improvements. So the EBNN algorithm reorganizes all the feature extractor and the fully connected and the pooling layers, and so that all of them can be combined into a fused block. So essentially in this network there are two fused blocks. One is the feature extractor block and another is the max pooling block. And also we chose the MNIST dataset for handwritten digit detection for these tasks. So let's look at how we offload the task to the DPUs. Now, there are some clever considerations we had to do for that. For example, if you think about the softmax activation layer, uh, it contains no linear computation. So it's not really ideal for a in-memory processor with low precision computations. Therefore, in this approach, we offloaded the convolutional pool block to the PIM. And after having that processed in the DPU, we took it back to the host and then performed the softmax. Now, and in this way, we could assign multiple processing threads per a single DPU for this particular network. And so another thing is that although the UPMEM PIM does not support baseline floating point computations, there's way we made a way around it. And the solution was to use the lookup tables. The lookup tables are created inside the DPUs by storing the pre-computed results of all possible operations, and that act as our floating point substitute. And so the way that lookup tables are formed is that the host uh, generates the results and then stores them in the MRAM. And during the computations, just those data are fetched right from the MRAM, and the computations are performed. And the next network that we implemented was the ELO V3. Now, the reason for choosing ELO V3 is that it's a very famous network that is able to perform real-time object detection with high accuracy. So the EBNN, the previous one, which was just a digit recognition, or it's just an image recognizer network, whereas ELO V3 can perform object recognition. And so it can detect, recognize objects and pinpoint where those objects are located. So as a result, it has a feature extractor block followed by a detection block, resulting in a very deep architecture that has 53 layers, 53 convolutional layers, sorry. And so for this one, binarizing the data was not good enough. So we had to resort to larger precision computations for particularly 8-bit fixed point precision computations all around. And also mm, for these tasks, the image sizes were much bigger. It is 416 by 416 each input. That's why we had to partition the images more aggressively across multiple DRAM chips and the constituent DPUs. And now this is how we implemented our large matrix operations. So first of all, we took a large gem function, that is a large matrix vector multiplication, matrix multiplication. And if you notice that there are four for loops in each code. So what we did is that we flattened all the loops and generated a stream of parallel operations, and then distributed those to each DPU. And since this is a memory bound operation, we needed a lot of memory usage. And so basically, this was a major performance bottleneck in this case, because when we had to access a large amount of data that and repetitive access of those data, that meant frequent access to the MRAM, and which slows down the performance. So let's have a look at how we distributed such large matrices across multiple DPUs. And this is our decomposition algorithm right here. The scheme we used is that, so if you have m DPUs, you should be using m number of, sorry, if you have m rows in the input matrix, that's how many DPUs we should be using. That was our optimum result. So I'll not go in deeper into the implementation, because the rest of the stuff was mostly mhm, finding coding solutions. And once we did that, this is our performance evaluation based on the implementation of both ELO v3 and EBNN in the UPMEM server. So the first of all, let's have a look at figure 17. And we can see that the performance of the DPUs increase respectively linearly and sublinearly, and then flatten with increasing number of threads. That by thread, here it is called tasklet. It's a term used to identify different number of parallel threads per each DPU in the UPMEM system. So when we keep increasing the number of threads in each DPU, we see that at a point we reach a saturation, and further increasing threads doesn't help. And this can be tracked back to the capacity of the MRAM and um, sorry, the capacity of the caches of the IRAM and the WRAM. And so let's have a look at figure 18, that even with multi-threading, there are different optimization techniques that we could apply to improve the performance. And these optimizations are built in the UPMEM toolchain. So the first one is no multi-threading and no optimization. And then we add multi-threading, and then apply both multi-threading and optimization, and we see the best results come up from there. So this is the recommended way to go for multi-threading in the DPUs. And finally, we can have a look at the growth of performance with increasing number of threads. So with respect to a standard CPU. And as we can expect, that the growth is linear, so that as we keep increasing the parallelization across the DPUs, the performance actually climbs up. So that's the core benefit of using a PIM over a standard CPU, and especially UPMEM system, because you can, with a server system, you can actually scale up as much as you want, ideally. So also we compared the performance of the UPMEM PIM with several other contemporary PIMs for a kind of a quantitative understanding of where it stands. So we compared with uh, DRISA, PPIM, Scope, and LACC. So each of these architectures have their own quirks. For example, the DRISA is a bitwise parallel processor that is aimed at also CNN acceleration. And a Scope, it uses stochastic quantization, stochastic computing for the same purpose. PPIM and LACC use lookup tables. Now, there is a distinct difference between these two architectures. However, all of them are different from UPMEM, which uses a RISC pipeline for the same purpose. Now, in figure 19b, we can observe that the UPMEM PIM has the lowest power consumption per chip compared to the other PIMs. And this is significant because DRAM chips are, they have a power budget, so we cannot just put as much processing capability in each chip as we want without some kind of modification or advancements for handling that kind of power. So and conveniently, all the others are actually academic work, so they're the modification or advancement of these works. uh, so actually, sorry, the DRISA and Scope have actually prototypes, and they have significant modifications to support the kind of power draw that this processing requires. So yeah, that's an important aspect, the power. However, with low power, there is a distinct disadvantage that the energy and energy efficiency is lower for UPMEM PIM for per chip. And so this is because of the large processing footprint, and also the fact that there can be only 8 units in every chip because of the large size. So the in terms of the area efficiency, we can say that achieving the area density is not the purpose of the UPMEM DPUs. That is because it is distributed across multiple many DRAM chips that are connected in server configurations. So overall, we can say that the UPMEM PIM is a safe and practical approach that has with a large overhead for the computation. However, in future, if we can make the DPUs more compact, we can gain in terms of performance. So that leads to the discussion of potential improvements. The first, I'll talk about the software domain. The first one is that the software of the architecture of the UPMEM is pretty developed for a very novel computer architecture, because everything had to be built up from scratch. And but there is room for improvement for user convenience. For example, there was some debugging problems that we faced that could be improved. And also, as I discussed previously, the 8 byte granularity of data, that is a limitation when it comes to allocating operations and tasks across multiple DPUs. Especially this happened for yellow v3, where we had to decompose the task so aggressively, and we had to every time align the data blocks. And so another recommendation is that supporting Python frameworks. And one way to do that would be like through OpenCL or CUDA-like frameworks that already have support for Python. And next, let's talk about the hardware domain. And so in this regards, we'd say that there's much room for development in the AI domain of the UPMEM PIM. And our takes are actually purely academic and conceived from our knowledge and experience of designing memory-centric accelerators. So there might be some limitations in our recommendation as well. But first and foremost, we would like to point out that the DPU's large footprint is actually a challenge in terms of improving parallel performance. So, for example, the DPU has a 3.75 millimeter square footprint, which is 3 times larger than a DRAM bank, which is at around 1 millimeter square in the 28 nanometer technology. And that reminds the other thing, which is the technology node. Right now, the DPUs are implementing the 65 nanometer technology, and I've heard that it's going to be scaled down in future. So that might be a significant point of performance, significant scope for performance growth, parallel performance. And because with smaller DPUs, we could place more of those, potentially twice as many in each DRAM chip. And so the other thing is the operating frequency. So we know that DRAM operates at a lower frequency than CPU or any other digital circuit because of the capacity latency of DRAM cells. But when the processing is happening inside the PIM, inside the memory chip, the processor itself is essentially capped by that frequency. So one possible solution is to go for high operating high frequency DRAM technologies, or if there would be a potentially a way to decouple the operating frequency of the memory and the processor, that would also be a potential solution, which has been tried in some academic research, but it has potential. And the other room for improvement was that we noticed, especially for AI computations, is the floating point support. Now, it doesn't have to be like large floating point. For example, we can go for the bfloat, Google bfloat, or TensorFloat. Those have low precision, such as 16 or 18 bit. but they are very good for AI applications. And so other potential improvement is supporting complex operations such as multiplication and divisions straight in the ALU. Because right now, as we worked on our implementation, we had to implement the compiler implemented multiplications using a stream of addition, which were issued as separate instructions. So if those are like, if there was a way to implement multiplications as a single instruction, that would probably be more optimized. And other than that, with the YOLO v3, we noticed that as we are talking about the saturation of multi-threading, so we noticed that the IRAM and the WRAM, the caches, they actually quickly get overloaded when data intensive tasks are issued. So one possible way would be to increase the size of those caches, and other would be to improve the DMA potentially, so that the latency of data access is lower. So, in terms in from our side, we'd love to further optimize our EOLO VG implementation, because we noticed that we added a certain amount of inefficiency when it comes to the segmentation of the tasks, and basically aligning those identical blocks to each DPU. That there's a way, there's room for improvement in that department. And also, we'd like to explore new mapping schemes, so that the tasks, so for example, we use the square, like rectangular segmentation. Maybe there's some other way to further improve the parallel performance that we'd like to explore. And further, we would like to expand our investigation of AI applications with other CNNs or other networks, such as VGGNet, residual CNNs, that is ResNet, and also CNNs with attention layers, or even the transformers itself. So that is our work so far, and thank you for listening to my presentation. Please let me know if you have any question.